Right, for the last talk of the morning session, we have Serena Patel tell us about cosmology with the SKA.
Okay, thanks, Roy, and thanks to the organisers for the invitation. So I'm going to talk about cosmology with the SKA, which is quite a broad title, so I apologise if you're an SKA cosmology person, I don't specifically mention the orbit, but I've kind of tried to pick some sort of some kind of key points, which I think are important. Okay, so Bernie gave a nice introduction yesterday to the SKA, and so I'll just kind of briefly go over the main bits. So the SKA is an international project to build a very large radio telescope. It will be built in 2 phases, and the idea is to get a total collecting area of about 1 square kilometre. So it's actually going to be made up of 3 separate instruments, and will cover a frequency range from a few tens of megahertz to tens of gigahertz eventually. I think it's important to point out that it's going to have a sensitivity and angular resolution that's never really been seen at radio wavelengths before, and so it really does open up the radio window for things like cosmological exploration, etc. And it's going to be co-hosted between Australia and South Africa. So I think it's also important to note that the SKA really is kind of, you know, amongst many things, it's a massive technology and engineering challenge. And so kind of in the kind of build-up to the SKA, there's quite a few pathfinders that are, you know, are being built to kind of demonstrate that the technology can actually work as we want it to. So there's ASCAP, which is the Australian SKA pathfinder, Cat7 and Meerkat, which is the South African prototype. There's also LOFAR, which is a low-frequency array in Europe that's also being built. The VLA and Merlin are both currently being upgraded. I think they've both finished and they're kind of in their sort of preliminary data taking phases now. And so all of these are important instruments for us to kind of get to know and understand in the lead up to the SKA. Okay, so as I said, it's going to be 3 separate instruments. So we've got SKA survey, SKA low, and SKA mid, and this is kind of just a summary of what they are. So surveys 36 ASCAP dishes plus 60 SKA 1 dishes. This is the frequency range. Low is SKA low is many dipoles that will be stuck in the ground, and that will be, you know, as the name suggests, the low frequency part of the array. And mid, which is what will be in South Africa, will be 64 Meerkat dishes and 190 SKA1 dishes. And here I've just outlined the field of view and the resolution at these kind of fiducial frequencies. So you see that SKA survey has got a large field of view, about arc-second resolution. Low has a large field of view, not very good resolution, and mid has a small field of view, but really excellent resolution because of its long baseline. So it's not just a cosmology instrument. Its key science drivers are sort of probing the dark ages and the epoch of reionization with the highly redshift 21 centimeter line, testing GR with pulsars and black holes, galaxy evolution, cosmology and dark ages is also part of that, but also understanding cosmic magnetism, and looking for new life and new planets as well. So just a quick note on the sort of surveys that are going to be done with the SKA. So, you know, you can do an H1 line survey, which is basically the radio analog of a spectroscopic survey. Then you can do continuum surveys, which is measure the sort of total radio emission in wide sort of frequency range, but you get no information on the redshift with those surveys. The kind of new novel kind of idea that you can do with radio telescopes is something called intensity mapping, where instead of resolving each galaxy individually, you take a very resolution map. And so it's almost like a pixelated version of this, where you just get a brightness temperature in low resolution pixels, sort of similar, if you like, to the CMB, but you get this at many redshift. So intensity mapping, I'm going to talk about a little bit, but I think Mario will talk a lot more about it in his talk later on. So for cosmology, I'm mainly going to focus on experiments that we've done with SK-MID and some with SK survey, kind of utilizing all three of these types of surveys that I've mentioned. So the things I'm mainly going to talk about are BAO, redshift-based distortions, and cleansing. And like I said, Mario will talk a little bit more about some other sort of cosmological things. Here's a picture. So this is what the sort of Australian side of the SK will look like. The dipole of SK low and the SK low dishes in survey. And again, once we put SK-MID into the Karoo, it will look something like that. Here's a car. Here's another car. The timeline. So 2017 for SK phase 1, so this is kind of incorporating the pathfinders into the early phase of SK1. We hope by 2020 we'll start to do early science with those. And by 2025 it should be all fully built and all fully working, hopefully. And sometime kind of in between here and here, people will start thinking about SK2 and hopefully by, I don't know, 2025, 2030 or something, we'll start building that. Just to kind of compare that with sort of current and future sort of optical things. We've got DES, which is currently going, Euclid, which launches around 2020, and NSST coming along sort of late 2020. So most of the stuff I'm going to talk about actually is work not just done by me, but by lots of other people as well. So this year we've been rewriting the SKA science book for our trouble. We all got to go to Sicily for a week, which was lovely. But yeah, so work done by lots of people, and it all forms part of the cosmology side. So, okay, so the first thing I'll talk about is the constraints that we can expect from the SKA and the BAO. So BAO is the number of times by people, and you know, it's this sound wave propagating in the early universe, and they leave a characteristic scale imprinted on the CMB and also on the late time galaxy distribution. So you find galaxy preferential cluster at this sort of 150 megaparsec scale. And so with a spectroscopic survey, you can hope to kind of approach sort of like what the Hubble rate is doing and the angular diameter distance are doing at various redshifts. So here's the current state of the art measurement of the BAO. This is off DR10 and DR11, and you can see the BAO bump here at 150 megaparsec. This is real space, and Fourier space that bump turned into a ball. So this is work done by Phil Ball and people looking at how well you can measure the BAO wiggles with various SK surveys. And what he's plotted here is what he calls FBAO, so he's just taken out the smooth part of the power spectrum just so you just see the wiggles at various scales. And these are the constraints that you would get from an SKA1 galaxy survey done with SKA survey, which will go out to a redshift of about 0.9. This is what you get from an intensity mapping survey done with SK-MID, which will go out to about 0.5. And then these are the constraints one might get from a full SKA. So this is your billion galaxy spectroscopic survey going out to a redshift of about 2. So you can see immediately the intensity mapping, because of the lower resolution, you can survey the sky much quicker. And so just because you get more sky coverage, it does much better than a galaxy survey. Likewise, you can see that the error bars on here are very similar to this one, and this is basically the prospects with Euclid. So you can see even by SKA1, the phase 1 of the SKA competes kind of with Euclid and will do much better by the time you get to SKA2. Another way of looking at this is by looking at the fractional error on this sort of average distance. And what Phil's plotted here is various configurations of the SKA in various experiments, along with BOSS, Euclid, and W-FIRST galaxy surveys. So again, you can see, if you look at the sort of yellow and orange line here, these are the SKA survey galaxy plots. And you see that they're not very competitive in comparison to the intensity mapping ones here in blue. But the thing that you do see is that the intensity mapping in SKA mid or SKA survey kind of give you competitive constraints to Euclid, which is this grey line here, at slightly lower redshift. And again, SKA2 does really, really well over a very, very large redshift range. So another way of looking at this is that, by the time Euclid does come along, you'll have some very nice constraints already from the intensity mapping SKA1 experiment. So propagating that forward to what you might get for dark energy. So this is for SK survey, galaxy survey, and an intensity map with SKA mid compared to Euclid and the full SKA. And this includes Planck plus low redshift BOSS data in this, and this is what you get for W0 and WA. And you see that although even the intensity mapping is not really competing with Euclid in terms of raw figure of merit, it does still provide this low redshift, this very good low redshift data set for joint analysis by the time you come along. And SKA2, as Bernie was saying yesterday, blows everything else up as well. Okay, so redshift-based distortions. So we've heard quite a bit about them, so I won't spend too long on this, but you have this galaxies falling in to overdensities, and the misinterpretation of the measured redshift. If you attribute the whole thing to the whole flow rather than including the peculiar velocity, leads to this distortion of the correlation function in redshift space. And here again, this is a nice demonstration of that from the BOSS survey. So this is the correlation function, transverse and parallel to the line of sight. You can see this flattening at large scale. So by measuring the correlation, the galaxy power spectrum, in redshift space, it's related to the matter power spectrum in real space via the bias and the growth rate. And so what Alvise's done for the redshift space distortion chapter is he's looked at how well you can constrain the growth rate, how the redshift space distortions can constrain the growth rate, and through that how well you can discriminate between different models of dark energy. So what he's looked at is he's looked at two cases. So first of all, parameterized growth, so parameterized in this sort of standard way, if you like. And what he's assumed is sort of redshift evolution for F, the bias, and sigma rays, and then the RSD is just giving you gamma. And then in this plane of gamma versus W naught, these are the constraints that are coming from intensity mapping with SKA mid and survey, full SKA, and again Euclid. So you can see again that SKA2 beats everything, but as I was saying with the BAO, intensity mapping will provide sort of nice sort of complementary data to the slightly higher redshift Euclid experiment, and that's kind of better seen in this plot, where here there's no parameterization of that growth rate, so we've just got the fractional error on F sigma 8 for, again, various different sort of experiments that one might do, and you end up with sort of similar interpretation of this plot to what I said before. So the galaxy surveys don't really compete with the intensity mapping surveys, but you see that the intensity maps provide very nice sort of low redshift results that might go along with what might come a joint analysis with Euclid, and the SKA, the full SKA, does significantly better over quite a large redshift range. Okay, so then the next thing I want to talk about is lensing. So I'm sure as you all know, you have sources sitting out in space, and as they travel towards you, the large-scale structure in between causes distortions to the light rays, and the manifestation of that is that you see distortions in the shapes of things. So we characterize that with the convergence kappa and the shear gamma 1 and gamma 2, which cause circular things to become elliptical, and here you get some change in the object size. So normally what we do is we assume that out in space on the source plane, things are randomly orientated, and then the shear causes a coherent alignment, which by measuring lots of shapes very accurately and doing statistics, then you can try and measure, and learn something about the matter distribution that's gone through. One of the nice things about the SKA and actually radio surveys in general is that they generally probe a higher redshift. So this is work done by Michael Brown. And here he's just plotted the redshift distribution expected for a 5,000-degree survey with DES and a similar size survey with SKA1. And you can see that the redshift distribution has a much longer tail to it at the higher redshift. And consequently, here's the measured lensing, the lensing power spectrum for those two surveys in 5 different redshift bins, and you see that the SKA can go to much higher redshift because of this tail. So what he's done is he's done some forecasts for constraints for the 2-year continuum survey. So SKA1 early, so this is about 50% sensitivity of phase 1 of the SKA, over 1,000 square degrees. And you see that, so these constraints actually are about an improvement of about a factor of 5 on the current best optical data set, CFHTLS. And again, as you go forward in time, the SKA1 with a 5,000 square degree survey, there's constraints on sigma, Hagen, and matter get smaller and smaller once you get to a 3 pi to radian survey with the full SKA. And I should say, actually, I forgot to mention that this actually accounts for errors in the photometric redshifts as well. So what I wanted to spend a little bit of time talking about is some of the challenges, some of the more technical details about how one's actually going to do these measurements with an instrument like the SKA. So I think it's important to note that we've never really done traditional cosmology, if you like, with radio surveys in the same way that we do with optical surveys. The two instruments are very different, and so, we need to ask ourselves the question, is it just as straightforward as applying the same methods and techniques that we have in the optical to the radio? And so, are there challenges? Are there any potential advantages? And I'm going to do this sort of as a case study with recleansing because that's what I work on. So we don't currently have any data, right? This is one of the first problems. There's very few sort of high-resolution, high-sensitivity radio data sets that one might try and measure lensing with. So one of the first things that we've done is we've tried to put together a simulation pipeline where we can try and learn about potential systematic errors. And so we've put together this pipeline where I can feed in a fake model of the sky with complex source morphologies, etc. And I can simulate those observations for a given interferometer with various sort of systematic effects, etc. And then we can compare the ellipticities that you put in versus the ellipticities that you get out. And this is work that I did for LOFAR and Merlin, looking at what happens when you point the telescope at two different declinations in the sky. You see that, you know, we seem to be doing quite well. If we put in some ellipses, I can get out something that's quite tightly correlated with what we do. So, given that we don't have any data at the moment, one of the things that we do is simulate the hell out of it. We did some work earlier this year for baseline design. Bernie kind of mentioned it yesterday. So this is kind of what the SKA mid phase 1 will look like. So we've got dense core, there's lots of points in there, and then these three spiral arms that stretch out to sort of give you baselines of about 170 kilometers or so. So these were the two proposed sort of last year or so. And one of the things that we did is we looked at how well can you recover the shapes with that kind of array of dishes, right? So here I've just plotted the true electricity that we put in, and then the difference between the true and the measured that you get out for these two different arrays. And as you the actual absolute value of them is not so important, but you can see that both of them give you very similar answers in this metric that I put here. One of the things that we asked ourselves was, could we possibly ask the SKA to change where they put their dishes if it made the recleansing shape measurement easier to do? And so I did various things, but this is just an example of one. So we said, okay, what happens if you take 9, 21, 30, whatever, a number of dishes, and you found the extra money from somewhere and then put them into the spiral arms? Are you able to recover the shapes better than if you didn't do that, right? So I've plotted the 2 points now, so I've plotted that calibration bias, multiplicative calibration, and the additive bias, M and C, and the red and the magenta point are just the two arrays that I showed before. And then these other colored points are just reflect the extra number of dishes. And as you can see, they're all clustering around the same point. So after a lot of simulations, we get to the most boring conclusion that actually small changes to the array design doesn't actually affect you at all. One of the important things that we're trying to use the simulations for is to try and get to where we need to get to for SKA1, whether it be early or the total phase 1 or SKA2. So you can basically work out this calibration, these calibration biases, and what you require them to be in order for your measurement to be statistics dominated rather than systematic dominated. Right, so it's just saying how well do you need to be able to measure these shapes. These current simulations that we've done for SKA, although not optimized in any way, are sitting at about 0.3 and 0, so M of 0.3 and C of 0, roughly. And these two columns here are giving you the requirements of various surveys done in various stages of SKA. And we see that even for SKA early, we're still sort of like an order of magnitude away from where we need to be in terms of those calibration numbers. And so there's a lot of work to be done here to try and figure out where these calibration biases are coming from. Can we isolate in our system, in our simulations, where the problem lies? So there's a lot of work that we're doing to try and understand that. One of the other things that we're trying to do at the moment is figure out how much of what we already know from the optical community and the lensing communities and groups there, and how much of it is applicable to us directly in the SKA. So an optical telescope is effectively just a big camera, right? So you have a galaxy in space that's been sheared, but on your CCD in your data it looks like this, right? I would argue that given that this is quite correlated with that, you can infer shapes and stuff, and I don't want to say straightforward because I know it's not straightforward, but there's a correlation there which helps you. Radio data looks like this. because you don't measure images, you measure effectively the Fourier transform of the sky sampled at the different spacings that you have in your array. So you need to go from here to whatever the gravitational shear is, right? And we know that the success of any weak cleansing measurement is in how well you can measure ray shapes. So we're setting up what we're calling radio break, which is going to be a blind sort of shear measurement challenge with simulated radio data that we want to supply to whether you're a radio astronomer or an optical cleansing astronomer, where you can apply your technique to the simulations that we give you, and hopefully we can see whether or not those techniques that they've developed in the optical are applicable here to radio data. So this is done in the optical. They did this in the optical community, and it's been running for about 10 years with real great success. For the SKA and radio surveys, the thing we need to know is, can we measure shapes directly in the Fourier plane? So can we directly infer the shapes of all of our sources from data that looks like that? Right? Or do we need to image that? Do we need to still make images and do lensing in the traditional way, if you like? There are some Fourier plane techniques now starting to sort of come out, and people are starting to think about this, not just in the context of lensing, but other sort of technology things as well. But they are very, very computationally expensive. So we need to, challenges like this are designed to try and address those kinds of problems. So we're hoping within the next year or so, we'll have a very nice sort of set of simulations that we can give to optical astronomers and radio astronomers, both in the image plane and in the sort of data plane, if you like, and hope and start to try and address questions like this. So one of the sort of nice things about doing stuff in the radio is you can get polarization information. So you have magnetic fields in the galaxies, and they cause polarized emission. Now, if you can measure sort of measure that polarization, then you can try and do a little bit better with lensing, because the polarization orientation angle is not affected by lensing. So it's basically giving you information for free about what the intrinsic shape of the galaxy was, if there's some correlation between the polarization orientation and orientation of the actual structure of the galaxy. And this has kind of been measured locally in the universe, and people think that the difference between those two angles is actually very small. So you can hopefully use this to remove intrinsic alignment, which is one of the sort of big key sort of systematic errors that we know about from optical lensing. So Michael Brown and Richard Bass calculated this in 2011, that you can maybe use this to reduce the shape noise contribution to the Lane power spectrum, and you get sort of an error in CLs that look like this. And so you get this alpha RMS, which is the scatter between that observed polarization orientation angle and the intrinsic orientation angle. And like I said, if this thing is small, clearly in the limit that it goes to 0, this whole term vanishes and your measurement becomes independent of that shape noise. But it may not be 0, it may be small, but we don't know. But it also depends on the number of galaxies for which you can get polarization information for. And these, these are kind of things that people have tried to look at locally, but what those actual numbers are is not yet clear. Similarly, you can do something with rotational velocities. So if you can measure the angle between the rotation of the velocity vector, then you can show, and it was shown in this paper here, that they should be perpendicular, and that when it gets lensed, that angle that angle changes. And so by measuring that angle, you can get information about the shear field at that particular point in the sky. But again, this has very similar problems to polarization in that, this getting rotational velocity for a galaxy is hard to do. So it's not clear if you will ever have enough statistics for this to be worthwhile. So there's always going to be this trade-off of extra information coming from either the polarization or the rotational velocity that help you with the intrinsic alignment and the loss of number statistics that you get, which it's just going to hurt you anyway. Okay, and so the last sort of, I think this is like one of the advantages of trying to do lensing in the radio, given that we already do it in the optical, is the synergy between the two. So if you have an estimator of shape, whether it be in the optical or the radio, then you can write that as a combination of the gravitational shear, which you're trying to measure, the intrinsic shape of the galaxy, plus some systematic contribution. Now, in a single survey, the correlation function has a contribution from the gravitational shear which you're trying to measure. Then you have these two intrinsic alignment terms, so the GI and the II term. So this is, the II is when you have two galaxies that are physically close together and they sort of align, and that mimics a lensing signal. The GI term is when you have, in the foreground, you have two things that are close together that kind of align, and that produces a correlation with the shear from something that's sat behind it. So, those two things are very difficult to understand and model. Plus, you have this systematic term, which in principle can be absolutely anything. So, the advantage of having two surveys at two different wavelengths is that you can cross-correlate the two, and you get the GG term, which is the bit that you want. You now get two GI terms, right? Whether or not these are the same in the optical and the radio, you have to measure and see. You end up with an intrinsic, but correlated between the two different things. So this is, are the shapes in the radio correlated with the shapes in the optical? And then you end up with this cross-systematic term, which presumably has to be zero, because you just wouldn't expect the systematics of one to be correlated with the systematics of another. You might potentially do even better if it turns out that the radio shapes and the optical shapes aren't correlated. So this is work I did a few years ago, looking at some Hubble deep field data, both in the radio and in the optical, matching the objects, doing shape measurement of them, and then just plotting the two against each other. And as you can see, they're not massively correlated. And so if this term is also small, then basically the cross-correlation between, say, Euclid and SKA will just mean that you're able to extract the cosmology that you want much clearer. Okay, so cosmology and dark energy are like a big part of the science case for the SKA. Even with SK in phase 1, we'll already start to make some very competitive cosmological measurements. The full SKA is going to make game-changing measurements of various things. And given this new technique of intensity mapping, we're going to start doing some novel science that's actually sort of, unique to the radio. Yeah.
Any questions? Yes.
Can you do lensing without measuring the shape of the galaxy, just with the intensity mapping? Because I guess
So there are people, because you can, it's like similar to the CME. Yeah. So I didn't talk about it, but yes, people are looking at that. Yeah.
What's the latest on that?
I must say I don't know.
I think it used to be numbers like 0.5 dB or so.
I haven't done the numbers in my head, but it's, I mean, it's, again, it's comparable to the fluid, so.
0.05, I think is the
I mean, we haven't fully explored the intensity mapping part. As you go to small scales, there might be an extra information there, but it's still like, it's still something that it's being calculated right now, so.
You said that the polarization is oriented like, or is correlated strongly with the original orientation,
Yeah.
the dual orientation of the galaxy. So you can use these to direct the deflection angle of individual galaxies?
No. So my understanding of it is that it still like depends on the kind of galaxy that you look at. So the kind of source that you look at, whether or not it's strongly positively correlated or anti-correlated. And so basically what it's telling you is about the intrinsic orientation of the galaxy before the length.
Yes.
Yeah.
If you know the intrinsic orientation and you see the relative orientation, so you can measure the difference.
Yeah. But
The refractive.
yeah.